Welcome to Math 1201 video number 9. In this video we're going to take a look at the cofactor expansion method for evaluating determinants. So far we've seen some methods for calculating determinants of 2x2 and 3x3 matrices, but what do we do for larger matrices, say 4x4 or higher? Theorem number 1 is going to answer that question for us. It's going to give us a method for calculating a determinant for an n by n matrix. And there are two formulas that I want you to copy down. The first formula we're going to use is called the cofactor expansion along row I. And that's given here as this first equation. So we have that the determinant is equal to ai1 times the cofactor ci1. Plus the entry ai2 times the cofactor ci2. And we keep doing this until we get to the entry ain and multiply it by the corresponding cofactor. The second equation is called the cofactor expansion along column J. So here, instead of choosing a row to do our expansion, we're going to choose a column. And that formula here is given as the determinant is equal to the entry a1j times the cofactor c1j plus the entry a2j times the cofactor c2j, and so on until we get to the last entry in that column, anj, and we multiply it by its corresponding cofactor. Now the proof for this theorem is not required for our course. If you do want to see how it's set up and how it works, you can definitely ask me anytime and I will be more than happy to show you. The nice thing about theorem number 1 is that these two formulas that you're going to see work for any size matrix, even 2x2 or 3x3. So what we're going to do next is we're actually going to do an example for a 3x3 matrix, and we are going to use those formulas that we saw. What we're going to do first is we're going to take this 3x3 matrix and do an expansion along row number 1. And then I jotted down the formula here. So we have a11 times the corresponding cofactor c11 plus a12 times its cofactor plus a13 times its cofactor. So here I've started to fill in some of that information from the formula up here. So a11, that's this entry. The 1 entry is number 1. And I'm going to replace this cofactor with m11. Because 1 plus 1 is even, I know that this cofactor is equal to the minor of the 1 entry. Next I move over here, so this a12 is negative 1. 1 plus 2 is odd, so I can replace the cofactor of the 1 entry with the minus of the 1 minor. And last, I replace a13 with 2, and the 1 cofactor with the 1 minor. The next step is to just simplify this expression a little bit. You're going to replace all of those minors, get rid of some minus signs, change them around if you need to. So here we'll drop the 1, we'll fill in the 1 minor. The signs here are going to cancel and give us an overall positive sign, and here is the 1 minor. And then we bring the 2 down and fill in the 1 minor. And your last step will be just to simplify these 2x2 determinants using the weave method. Each of these 2x2 determinants are going to give us 0. So our final answer for the determinant of A is going to be 0. What I want to do is I want to show you what the cofactor expansion looks like if we use a column instead of a row. So let's calculate the determinant of matrix A once again, but now we're going to go along column number 1. So in this case, the determinant is given by this formula. So we're going to get a11 times its corresponding cofactor plus a21 times its cofactor, and finally a31 times its cofactor. So once again, your first step is going to be to fill in all of those entries, a11, a21, a31. In this case we get 1, 0, and 3. And then we're going to replace the cofactors with either a positive minor or a negative minor. The only one that is going to be negative as we do our expansion along column 1 is C21. That'll give us a negative M21. Now something neat happens as we do our expansion along column number 1, and that is we hit a entry, the A21 entry is equal to 0. So in this case we're only going to have to expand out 2 minors. The middle one just disappears. So here are those 2 minors. The first one is M11, that's 0, 0, minus 1, 2. And the second one is M31, that's negative 1, 2, 0, 0. And when we expand out these 2 by 2 determinants, we just get 0 and 0 for a final answer of 0 once again. Now I wanted to do an expansion along row 1 and column 1, first of all to show you that we get the same determinant whether or not we expand along row 1 or along column 1, but also to show you the power of theorem number 1. Theorem 1 says that we can use any row or any column that we want when we're doing our cofactor expansion. So essentially, we should choose the row or the column that contains the most zeros. This is because we have to multiply by the Aij entry. So the more zeros that we hit along the way, the fewer cofactors that we have to deal with when expanding to find our determinant. So I want to revisit that first example one more time just to clarify the note that I just gave you. So if we take a look at this 3 by 3 matrix, which row or which column contains the most number of zeros? Definitely row number 2 is where we want to do our expansion. If we do our expansion along row number 2, we're going to hit 0 for every single entry. So as we come to here, we're going to get 0 times the 2, 1 cofactor plus 0 times the 2, 2 cofactor plus 0 times the 2, 3 cofactor. And our final answer for our determinant is going to be 0. And this leads us to a really nice theorem. Theorem 2 says if we have any square matrix that has a full row or a full column of zeros, this matrix must have a determinant equal to 0. I have 2 more examples that I want to show you to round out this video. The first one is that we're going to show that the weave method and the cofactor expansion method are equal for a 3 by 3 matrix. So what I've done is I've written down a general 3 by 3 matrix with the letters A through to I. And we're going to calculate the determinant of this matrix A using a cofactor expansion along row number 1. So here I've written out the cofactor expansion formula along row number 1, and I'm going to fill in the entries A11, A12, and A13. Those are going to be A, B, and C respectively. The only minor that's going to have a negative sign is M12. The other minors are going to be positive. That's because 1 plus 1 and 1 plus 3 are both even. So the next step is to fill in the 2 by 2 determinants that represent those minors. So for example, M11 is going to be EF, HI. And we're going to calculate those 2 by 2 determinants by using the weave method. So in that case, we're going to get EI minus FH. And if we do that for the other minors, we get this line right here. And our last step is just to expand out through those brackets. And this is the expression here at the bottom that we're going to get. And you can double check that this is exactly the expression that I gave for you for the 3 by 3 weave method. So what we've done is we've shown that cofactor expansion and the weave method are the exact same for a 3 by 3 matrix. They will end up giving you the same answer for the determinant. Alright, here it is, our last example of the video lecture. What we are going to do is we are going to use the cofactor expansion method on a 4 by 4 matrix. So in this case, we're going to try to figure out whether or not the matrix B here, which is 4 by 4, is invertible. And we're going to do that by calculating the determinant. Now what I'd like you to do is take a look at this 4 by 4 matrix and figure out which row or which column would be the best one to choose to do our cofactor expansion. Oh my god, it's a crazy dog! So if you decided on row number 4 or column number 2, those are the best choices. So here I've gone ahead and I've written out our formula for a cofactor expansion along row number 4. So here we have B41 times its cofactor, B42 times its cofactor, all the way up to B44 times its cofactor. Now we're going to replace all of these entries with the corresponding numbers inside that matrix. So here we'll get 0, -1, 1, and 0. Now we're going to have two negative minors in this case. So notice that 4 plus 1 is odd, so that's going to give us a negative minor. Also 4 plus 3 is odd, so this cofactor will be a negative minor. The other two are going to be positive. And lastly, I'm just going to get rid of any of those minors that have been multiplied by 0 and simplify these two up. So I'm just going to leave this as negative M42 and this one as negative M43. Here are those two minors that we get from deleting the information in row I and column J of our matrix B. Now what I want you to do when you get to this step is put a little bit of space in between these minors or these determinants that you get, because we're going to use the weave method to finish off the question. So I've gone ahead and I've started the weave method for that first 3 by 3 determinant that we have to calculate. So I've put the two columns on the right hand side, and I've calculated the first three products as -3, 1, and 2, and the second three products are going to be -3, -1, and -2. Now let's do the same thing for that second 3 by 3 matrix. So here is the weave method for that second 3 by 3 matrix. So the products that we're going to sum together are going to be 0, 0, and -4. And the products we're going to subtract are going to be 0, 2, and 0. Now I also forgot a minus sign way up here beside this 3 by 3 determinant, so if you could fill that in and just follow that down, that would be great. I also notice I've added in some rectangular brackets here. I use rectangular brackets just to remind me that it's all of these terms in here that are part of this 3 by 3 determinant. And everything inside these square brackets is part of this 3 by 3 determinant. And what we're going to do next is we're going to simplify all of the terms inside those brackets and get our final answer for our determinant. So when I fully simplify everything inside the first set of square brackets, I get 6. So that first term we're going to get is -6. Inside the second set of square brackets, I get a -6, so we're going to subtract off -6. So we get -6 plus 6 for a final determinant that's equal to 0. This tells us that B is not going to have an inverse because we found that its determinant is equal to 0.